Okay, so we continue from where we left off uh, in the last class. So in this case, in today's class, we will be calculating the viscosity of gas from uh, microscopic quantities like the distribution function. What I want to emphasize is here we are considering gas molecules which move at high velocities and undergo collisions, which is accommodated or incorporated in the theory through the single relaxation time approximation in the Boltzmann transport equation. And in the expression for energy, we do not consider potential energy. So there are collisions, instantaneous collisions, and that redistributes the distribution function and tries to bring it towards the equilibrium distribution function. But of course, here we are considering fluid in a steady state motion. Yeah. And since we are not considering interaction, it is necessarily the calculation of viscosity of a gas, and that's why I've written gas in capitals, and we shall discuss about this more soon. So whatever calculation I'm doing is not valid to calculate the viscosity of liquid. Uh, Before we go on, let me tell you that this is from Rice section 13.8 and 13.5. And the reason I mentioned 13.8 before is the first part of the calculation or this treatment is from section 13.8. 13.5 has a similar treatment, but that's from a different perspective. It's the path integral formulation. We are not going into that because we want to have only a relatively short discussion on Boltzmann transport equation. So we can't cover all of it. And this class again depends upon the singular relaxation time approximation. There can be also the collision term in the Boltzmann transport equation can also be considered, where we consider the correlation between velocities of two colliding gas particles where after the collision. But we'll discuss this point very briefly in the next class. But for this class, we still rely on the simple form of the collision term in the Boltzmann transport equation. And then if we did the full calculation with where we consider more details of the collision and the correlations of between the velocities after a collision, well, we can write down the term, but that needs more sophisticated approximation tools, and it becomes more intense, which we shall leave for a future stat phase course if and when relevant. Okay, so to begin with, we are talking about a flow profile of a gas, and what we have, it has reached the steady state, which means that suppose there are suppose that there are some boundaries, there's two plates, and they are moving in opposite direction with constant velocity. They are somewhere farther apart. It's beyond the diagram. So they're moving in the x direction, say here, somewhere here, or farther apart in this direction with a constant velocity. And the other plate is moving in this direction again with a constant velocity, the minus x direction. And the velocity gradient, as you see, is dvx dz. So as you go along z, at different layers are moving with different speeds. We have assumed that the system has reached steady state. So the velocity on any layer at any particular z value is not changing as a function of time, and the velocity gradient is not evolving as a function of time. Why do I say that? Because if you had a stationary fluid and you start moving the two plates, then initially the layer of fluid which is sticking to the surface, the moving surface, the moving boundaries, they are going to start moving. The fluid and the center between the two plates are going to remain static, but slowly as the fluid next to the surface starts moving, it is going to drag the next layer of fluid. Suppose this starts moving and it is going to drag the next layer of fluid. So this will slowly start accelerating. And this in turn will drag this layer of the fluid and so on and so forth. But after a certain point in time, steady state will be reached such that the different layers of the fluid move at a particular z value. They move with a constant velocity, but different layers of the fluid along the z direction, of course, have different velocity, and so a constant velocity gradient is maintained, right? So the other thing to keep in mind is this layer of the fluid, say, is moving with a constant velocity, but this layer of the fluid is dragging, is transporting momentum, is transferring momentum from here to here. I mean, if you like, it's applying a net force because of the velocity gradient, and it's trying to accelerate this layer of the fluid. So particles are basically going from this layer to this layer, because, you know, and each layer particles are moving in all possible directions. When we say about the fluid velocity, we are talking about the mean velocity of a large number of particles in a certain volume. The same concept as the velocity distribution function, the velocity fluctuations um, about the velocity fluctuations about the mean velocity. So this velocity could be 1 meters per second, but the gas molecules are traveling at 2000 meters per second or 1800 meters per second, right? So we are really and some of them are moving to the left, some of them are moving to the right. But if there's a velocity a finite velocity of this layer, it means a slightly larger number of particles are moving in the x direction, and they have a net. Uh, yeah, so a slightly larger number of particles are moving in the. They have a slightly higher velocity, uh, or a slightly larger number of particles are moving in the positive x direction, and so that when you average over the velocity of the distribution function, you average over the velocity of different particles, you get a net mean velocity of, say, 1 meters per second, of 2 meters per second, which will be represented by u bar x. You know, just as in previous class, we were discussing about this is the velocity of the individual particles, and they are traveling, and Vx minus Ux bar is essentially the fluctuation of the velocity above the mean velocity of the fluid. The mean velocity is calculated by averaging over all the particles which are considered in D3R, a small volume within the fluid, right? So as they are moving, so particles are going to move from this layer to this layer. They're going to transfer momentum from this layer to this layer, and that is going to create a stress or a net force, because there's a momentum transport per unit time, per unit area. There's going to be a net force acted upon by this layer to this, on this, right? But an equal and opposite force will also be acted upon by this layer on this layer, right? So basically the forces will cancel out. So there's a certain amount of momentum which is transferred from here to here, but then a certain amount of momentum is also being transferred from here to here, or you could say that a certain amount of negative momentum is being transferred from this layer to this layer. So that also is creating some shear stress. Shear stress means force momentum transported per unit time per unit area. And hence, this layer is not accelerating because the two forces from the two layers, one on top and one on the bottom, the upper one is moving with a higher velocity. The bottom one is moving with a lower velocity. So that is going to get cancelled out. So if you have a problem discussing with respect to this layer, this fluid is moving in the opposite direction, right? So negative momentum transport, if you like. I mean, if you are sitting in the velocity frame of this layer, right? So that's how that's and each layer, once you have reached, so this layer, the top layer has some value of u bar x, but the middle layer will have a different value of u bar x, and the bottom, this layer will have a different value of u bar x. And what is the point? The point is that once particles have moved from here to here, that will disturb the local distribution function. But due to collision, it will try to collision between particles in a certain volume. It is going to try to come back towards its equilibrium distribution, right? So that's the kind of discussion we also had in the previous class. The same idea is also going to be used here. And so while one layer, I mean, so the boundaries, you're pumping in energy and you're pumping in momentum. That's why this different layers are moving. But at a particular layer, though momentum is being transported, each layer is moving at a constant velocity once it has reached the steady state. Yeah, before that is going to be accelerated, but finally a uniform velocity gradient will be maintained, and the value of the velocity gradient will be essentially dependent upon, of course, the force applied and the viscosity of the fluid. For the same amount of force applied, if you have different viscosity of the fluid, in this case a gas, because we are not going to consider interactions when we calculate the stress tensor, which will in turn depend upon the momentum transport, the force acting, and so on. So in the stress tensor, we are not going to consider contributions from the interactions, the potential interactions between particles. The expression for the potential interactions, the contributions to stress due to interactions between particles, will be considered in a matter of 1 or 2, 3 classes more by the so-called the virial. But as of now, we are just considering gases which are moving at high velocities. The potential energy, the potential of interaction is neglected, and all that they do is undergo collisions. That's the only time the particles see each other, right? So that's why it's a gas. And moreover, I mean, the behavior of viscosity, we're going to calculate microscopically. We're going to have an expression for the viscosity, and you're going to see that the viscosity increases as per the expression, as per the approximations used, the final expression that we will get using the Boltzmann transport equation, using the the single relaxation time approximation. The viscosity, you will see, is proportional to kBt, which means if temperature increases, the viscosity of gas increases. So the viscosity of the fluid is a function of temperature. More temperature, more collision per unit time. Particles are going to move at higher velocities, right? And if you remember the beginning of the previous class, basically the collision time depended upon the mean free path divided by the velocity, right? And mean free path in turn depended upon the density of particles and the scattering cross section sigma 0, which is pi d squared. The where d was the diameter of the molecules or atoms, assuming them to be spheres, of course. So what is the point? So the point is, if the temperature increases, the average velocity of the particle increases, the average speed of the particle increases, not the velocity, because of the direction. So whole kinetic energy increases. So they basically undergo more collisions. If they undergo more collisions, and there'll be more also transport of momentum from one layer to the other, and so on and so forth. And so stress will increase, and viscosity will increase with increasing temperature. And that's the characteristic of a gas, right? Whereas for a liquid, the behavior of viscosity with temperature is different. If you increase the temperature, the viscosity of a liquid decreases. That you might see very easily uh, if you are using oil, and when you heat oil, you see it's going to move. It starts to move much more faster. But viscosity of oil again is not the right description, because oil is a complex fluid. There you have elongated molecules and so on and so forth. So the physics of the decrease of viscosity, the rapid decrease of viscosity with temperature. Yes, it's a liquid, but the physics is more involved than just talking about effect due to forces. So, of course, there is effect due to forces there also, but it's not a simple fluid. Water, in that sense, or some other organic solvents, in that sense, can be considered a simple fluid. By simple fluid, I mean there is interaction between the water molecules, but the water molecules can be considered as units. I mean, they have the water molecules, the degrees of freedom of position and velocity. Whereas oil not only has individual, so they are elongated molecules. So you have also conformational degrees of freedom to take care of. There can be entanglement and many other things. So yes, this is viscosity of gas where there is no interaction, potential interaction, and then you have viscosity of simple fluids, where you can still consider the individual molecules to be composed of, even if it is two or three, like water. You can still specify them by positions and velocities and interaction between the liquid molecules, where the molecules itself have their own. Whereas the next layer of complexity is complex molecules, where they're elongated or they're interacting by more complex mechanism than that of a simple fluid. There, the discussion of viscosity will also need to take other degrees of freedom, like it might, for example, have to consider the conformational entropy and so on and so forth. So, so, so that's why I want to say. But anyway, I mean, if it's a liquid, interactions are important, and viscosity essentially decreases with increasing temperature. Viscosity of a gas increases with increasing temperature. So these are the background physics that you have to keep in mind. You have to keep in mind the approximations that we are using. Just because we do a calculation, get an expression for the viscosity of a fluid, doesn't mean that you can understand the phenomena of viscosity coming from microscopic quantities. The same formula is not valid for a liquid. There, the physics is different, and you have to incorporate the relevant aspects, in that case, the interaction, to correctly describe the viscosity of a liquid, which we are not going to do in today's class, right? So that's the big picture before we go down deep into the maths. Right, so these are so one has to keep in mind the assumptions that we are using, and typically in my class I make I try to point out the assumptions in a much more explicit way than maybe other courses. I don't know. Anyway, so with this in mind, we're talking about the Boltzmann transport equation, which basically looks like this, right? This is the collision term, and we are using the exponential relaxation time approximation. We are assuming that there's a driving, external driving, which in this case is momentum. I mean, different layers of fluid are moving with different velocities, which is changing the distribution function from its equilibrium distribution, but that change f minus f0 being the equilibrium distribution function, is relatively a small quantity. And what this does is it constantly aims to drive the f, the changed distribution function. It tries to drive it back or relax it back towards f0 in a time given by this relaxation time. But why does it keep, why does f remain away from equilibrium? So left to itself, f will always try to relax back to equilibrium, the equilibrium distribution function of distribution of velocities. But because there's an external driving, f remains away from f0. So it's a constant balance. That's what is happening. So here the f0 for a particular layer of fluid, for a particular r, can be written as g. Okay, for unit volume. Yeah, else you would have d here. So f0 for a unit volume, this function will look like Vx, the velocity of the gas molecules, minus u bar x. This is the mean velocity of the fluid at a particular z. And you assume that in the y and the z direction, there is no particular net fluid velocity. So this will look like, I mean, you say that this is a small quantity, u bar x is a small quantity, and compared to Vx, the velocity of the gas molecules individually. And the equilibrium distribution function will look like m beta, like m by 2 pi kbt, if you like, if you remember the Maxwell-Boltzmann distribution, to the power 3 by 2, if you have 3 dimensions, and e to the power minus m beta by 2 Vx minus u bar x z by whole square plus Vy square plus Vz square. So this is an expression of the kinetic energy, remember, right? And yeah. So that's the expression of the kinetic energy. Now this will be there even for a liquid, right? What will be different, however, is the momentum transport. So this expression for the distribution function, this depends only upon, you know, the velocity coordinates when you wrote down the partition function or whatever, right? So it comes from the because the kinetic energy, it can be written as Vx square plus Vy square plus Vz square, and there's no dependence upon x. So this distribution function basically came from the that the kinetic energy depends only on the velocities, and it's quadratic. It's quadratic in the degrees of freedom, that is Vx square plus Vy square plus Vz square. And here we are considering the fluctuations about the mean velocity of the fluid, right? So that's the equilibrium distribution function. But since x, the velocity of the fluid in the x direction, is changing along z, so f is now a function of z. right? So there are changes in F along the Z direction, right? We are assuming steady state. There's no time dependence in F. F at each layer has a certain value. Moreover, we are considering no external force between layers of the gas, which means that, of course, on this layer of the gas, you have forces coming from there are momentum transfer from the upper layer and the bottom layer, positive and negative, uh, but they cancel out in a constant velocity gradient. And if there was a net force acting in the x direction on this layer, then it would accelerate. But it's not accelerating, which means the force acting from the upper layer and the force acting from the bottom layer is exactly the same. So they cancel out. So there's no net momentum. There's no net force acting on a particular layer. Hence, it's not accelerating along the x direction. So that's why we are saying there's no external force. In the previous case, there was this external electric field which was constantly driving the accelerating the charged particles, right? So we don't have an external force like that. So this equation, the Boltzmann equation, the right hand side remains the same. There is no explicit time dependence, so del F del T drops out. There is no external force. There is no acceleration and any layer of the fluid. So this term drops out. The force is acting on only the boundaries, and we are considering the fluid flow uh, away from the boundaries. So, and F is a function only of Z, right? F is a function only of Z. It's changing in different layers of the fluid. So this R dot into dr. So what is R dot? R dot would be something like Vx into del F del X, Vy into del F del Y, Vz into del F del Z. Right? Now del F del X and del F del Y are equal to 0. There's no F is not changing in the X and Y directions. The only change is along the Z direction. So the Boltzmann transport equation becomes Vz, right? So it becomes Vz, yeah, into del F. What is F? F plus F1, which F is changing as a function of Z into del del Z, right? And that is equal to minus F minus F0 by tau 0. Now, F minus F0, we write it as that's the deviation from the equilibrium distribution. That is referred to as F1, and this is the relaxation time, if you like, right? Okay, so assume, so if you assume that the change in ux with z, the velocity gradient is relatively small, it's much smaller than ux, then this change in f1 also, so f1 is a small quantity, and moreover, the change in f1 with z is going to be even smaller because f itself is changing very slowly. And now you are asking about del f1 del z. So del f del z itself is small, and then this is even smaller. So on the left hand side of the equation, we're going to neglect del f del z. But del f del z, so vz into del f del z is actually equal to f1. So we can't neglect it. So we are not talking about how f1 is changing as a function of z. So this is a small quantity. And this small quantity is equal to the small change in f along the z direction into vz. So that's the equation. So this equation now becomes vz del f0 del z minus f1 by tau 0. Now, where are we heading for? Where are we heading? So we are going to do some algebra, but let me tell you where we are heading. So to calculate the viscosity, we need So we need to compare it with the macroscopic equation, which is the stress acting. Um, uh, Suppose the stress, so this is the z, so the velocity, so it's moving along this direction. The x component of momentum, which is transported perpendicular to an area, and the normal to the area is in the z direction. So we are really interested in talking about momentum transport, momentum flux. So this is the area. There is an x. Because of the distribution function, as the particles cross this area, they are going to transport x momentum across this area. So x momentum px is being transported in the z direction, and that is going to give some stress, some amount of force is being transported per unit time. Some amount of momentum is being transported per unit time, which means some force. There's a net force acting on one layer of the fluid, or from one layer of the fluid to the other per unit area. That's stress, right? So, if you remember, somewhere we are really talking. So this is again stress, and we have to write it in terms of the macroscopic equation. Is this stress is eta into del b del x. So from the microscopics also, we need to have a microscopic expression for the stress tensor coming from the distribution function, but that we have to write it in that form as the macroscopic equation. And uh, and then when we write the amount of momentum transport from the microscopics, and that we show that it is proportional to the velocity gradient, whatever is the proportionality constant, which will depend upon microscopic quantities, will be the expression of the viscosity. And we're going to associate the macroscopic quantity, the average quantity called viscosity, in terms of microscopic quantity. So that's where we are heading. So we have to write the moment expression for the momentum transport, then rewrite it so that we can write it in terms of F1 and calculate the entropy. So here we have an expression for F1. F1 equal to, just taking the tau this side, is minus tau 0 Vz to del F del Z, right? Yeah. And this del F0 del Z, because we neglected del F1 del Z, this tau 0 Vz, so there was a negative sign here, which is from here. We are writing del F0 del Z in terms of del F0 Ux, right? As a function of Z. And so what is this Ux? This is essentially the fluctuation of velocities of individual particles. You remember Uxi with this tail, right? We are going to write it as del F0 del Uxi, how this quantity is changing, how the distribution is changing along Z, and then this would be del U, the same del U with a tail, the fluctuation del Z, and that in turn, but you know, Ux equal to Vx minus U bar x. So del Ux del Z, so this Ux, the same as this one, equal to minus del U bar del Z. So that del Ux del Z, this one we have substituted in terms of this. And what is this? This is the velocity gradient. Right? This comes with a minus sign. Hence, this minus sign and this minus sign cancel, and you don't see any minus sign here. So there is no minus sign here, right? So that's what's happening. So you're writing del f0 del z in terms of the fluctuation about the mean fluctuation of individual velocity of individual gas particles about the mean, and that in turn you're writing in terms of minus del u bar del z. This is the velocity field if you write, right? And this is the velocity gradient because you're writing the mean velocity change with z. Now, this expression for F1 we are going to use after a few steps. So we're going to keep it here. And what we are calculating here is the momentum transport along the z direction, the momentum transport of x along the z direction. So the area is this, and the normal to the area is z, and how much momentum is being transported. And that is, as we discussed in the last class, mvx. So chi here is mvx, right? Uh, uh, and yes, so the question is, wait, so let me, so the flux of chi along z, so the flux of chi, the net momentum transport along z is the chi into vz, right? And here chi, the net momentum being transported, the fluctuation that is being transported is Vx minus u bar x. So this is the fluctuation, right? So that's the amount of momentum being transported from one layer to the other, because particles are moving. So, so this was the fluctuation about the mean velocity, and these particles are going to move to the next layer. So hence, the momentum transport here, just think about it. You can find it in 13.18, right? Is m d3v f0 plus f1, okay, vz into, this is the amount of x momentum which is transported across the layer, right? So flux of chi by motion of gas particles in the vz direction, the quantity chi is being transferred along z in unit time per unit area. That's the idea, right? Yeah, so particles are moving in the z direction, and of course some particles can move not exactly in the z direction, they have a component, so they might be moving in all possible directions, but what is going to matter is the component, right? So here it's vz and f, we are going to take over all velocities, but then you have to worry about how many particles are moving with velocity v, suppose, so a particular v, and it has a certain vz component. So you're going to take that into account while calculating this, right? This quantity. So just to remind you that what was the distribution function? If you integrated over d3r, you would get the number of particles in volume d3r moving at position r with velocity v and v plus dv, or velocity v vector if you like. Similarly, however, instead of integrating over d3r, integrated over d3v, right? Then you would get number of particles in unit. So by this, what you have done Well, here you have integrated over all R. That would mean that number of particles moving all over the space with velocity v vector, because you have integrated over R. So it's not true that in volume d3 are moving at R. So since you have integrated over all space, which means that over all space, how many particles are moving with velocity v vector? So this thing is a bit erroneous, right? And similarly, however, if you integrate over all velocity vectors at a position r, it means the total number of particles at r in unit volume. That's the number density, because you've integrated over all velocities at a point r. Here, for a particular velocity v, you have integrated over all space. So it's the total number of particles moving over all space with velocity v vector, not in volume d3r and moving at r. There's no, if you integrate over r, it can't have dependence on r, right? So this is wrong. I'm sorry. And here, similarly, at a certain point in r, you have integrated over all velocity. So this would give number density, right? And the net motion in z direction will be f vz d3v at r. You have integrated over all velocity vectors. So some which are mainly moving, suppose in the x direction, it will have a small component in the z direction. So f, so number of particles, so this vz for those will be less, right? The number of particles moving with velocity in the x direction with a certain vz component, small vz component in the z direction. So here the contribution will be less. As the particles which are moving mainly in the z direction, so all the particles are going to contribute a larger number. I mean, depends upon the value of vz, of course, in the momentum transport in the z direction, right? And so this is the net motion in the z direction per unit time. Yeah, but the macroscopic stress tensor, momentum transport per unit time, force per unit area. Yeah. So now the stress tensor, which is basically the momentum transport, the x component of the momentum transport in the z direction, right? That's the momentum transport per unit time, per unit area. The macroscopic expression of like sigma zx. So how much x momentum is being transported in the z direction, that can be written as minus eta, eta being the viscosity with a minus sign, del u x del z. Why del u x del z? Because if the direction of del u x del z is in the positive direction, so that u bar x is increasing in the z direction, the gradient is in that direction, then the momentum transport, the next momentum transport is higher on the for higher values of x, and it is being transported in the negative direction. So the momentum transport is in the direction opposite to that of del u del x, hence minus. So the stress tensor, so that's the macroscopic expression for the stress tensor. Now our aim is to write the microscopic expressions sigma zx in a form so that we can compare the macroscopic and the microscopic expression, and if it also has del u bar x del z, then whatever is the remaining part, I mean the terms which correlate this with del u del z will be the viscosity, and we're going to use that. So sigma zx equal to m momentum So m into vx minus u bar xz, this is the net momentum. So the fluctuation in momentum which is being transported in different directions in the direction of vz, so many particles. So f0 plus f1 into vz, uh, integral over d3v is the number of particles moving across the surface area in the z direction, and it is carrying momentum m into vx minus u bar xz in the positive z or the negative z direction, depends upon how you look at it from in different directions. And this is essentially f, right? F is a distribution function d3, and that is of course can be written as f0 plus f1. And if you consider now this equilibrium distribution f0, right, it's ux whole square, that's the vy whole square, vz square, and e to the power minus m beta. So we have assumed this to be the equilibrium distribution. This itself can be proved. But if you look at this distribution, then you would see that an equal number of particles are going in the positive direction as in the negative direction, right? So if you integrate f0 over vz, right, ux also, I mean, so even the x component, there's an equal number going up, going up. So once you look at ux, this is symmetric with respect to ux, right? So if you take this integration with respect to f0, where vz is an odd function, ux is an odd function, it's going to, on an average, give 0. So the only term which is going to contribute to the net transport of momentum in the z direction, net transport of ux, I mean, like m into m into, this is the fluctuations, these are the things which are moving across different layers, that is going to be contributed by f1. So this integral, we have used also here a transfer of variables from dvx to dvx. So 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 what we have done is, yeah, so we have also, what we have also done is, del ux equal to dvx on one hand, but del u del z. So all the dependence of del ux on z comes from this expression, right? So it comes from this. So hence we have used, so we have substituted this as ux, and uh, on one hand dux equal to dvx, which we have also used and written this as dux here, right? We have used a transformation of variables both here and here. But now, once you have, so this d3v can be also written as d2v into dux. Now we are substituting the expression of f1 from previously, from essentially here, we had used it here. And if you look at that, then this del u bar x del z is also appearing here. And this is the expression on the right hand side is sigma zx, the same as the macroscopic equation. And hence this quantity eta, uh, and note that there's this minus sign, has to be, so this minus sign is here essentially, has to be equal to d3v tau vz, and there are two vz here, so that's why vz square, and you have a u bar x, sorry, ux sitting here, ux sitting here from, basically we have used this variable transform here, ux, this is the one with the tail, so it's really vx minus u bar x, so that's sitting here. So this is the expression we need to now calculate, right? Now what we are going to do is, I have written d3v as Uh, we have written d3v as dvz, dvy. Now here you have vz sitting here, m is sitting here, tau 0 is here. It's a relaxation time. Does not depend upon the values of vz and ux and so on and so forth. And the integral, now vx can vary from, in principle, from minus infinity to plus infinity. So that dvx we are converting to dux, and there was already ux sitting here, which we have kept here, and we have del f del ux, which is a function of z sitting here. So this integral, where we have a derivative with respect to f, we are going to use integration by parts. And just to remind you, the integration for parts, sum of two functions, integration of the product of two functions, sorry, not sum, product of two functions into dx, except we are not integrating over dx here, but we are integrating over dvx, which we have written as dux, right? So take v to be del f0 del ux, and this ux is the same as u. Then if you break it and work it out, and you can just look at Rife equation 13.510, then what it does is it has an integral over del f del ux, and this is again del ux. So what you get, so this dx is actually del ux, right? So this is one, this is one, this is this is one of the terms in the product, this is the other term in the product, the integral is over dvx. And when you do that integration by parts, you see that something which was del f0 del ux can be written as f0 integral this dx is the same as del ux or del vx. This minus sign comes here. This term will give 0. So what you have in turn is d2v f0. Remember, in the previous expression, you had del f del ux, but by integration of parts, it has been converted into f0, whose expression we know dz is intact, del ux is there, is this same as this. So because there was an integral here, thereby the del f del ux became f0 here, and you can refer to this. So what you have is a pretty simple expression. Remember, this came from this entire black part, the symbols, the terms written in black are coming from f1, because f0 integral this 0. So that was the origin. And finally, we have d3f f0 vz whole square, right? Now, what is f0 vz whole square d3v? That is nothing but this is just the expectation value of vz whole square. That's what we have been doing, and this is the equilibrium distribution, remember, and this is integrated over, you have basically n into vz square. This is the expectation value. Now what is the value of vz square? By equipartition, of course we did equipartition before. Yeah, so here we are using statistical mechanics, which came after the Boltzmann transport equation. But for simplification of things, this had to be proved using some more advanced Boltzmann transport equation. So we are using this. We said whole square is kBt from equipartition. So the expression of viscosity of a gas is n, yeah, kBt tau 0. Tau 0 is some internal relaxation time, This has been replaced by KBT, and note that viscosity increases with so viscosity increases with the increase of temperature, with increase of relaxation time, and the increase in the density of number density of particles. Uh, Note, this seems to be a fantastic theoretical exercise, but to calculate the viscosity of gases, you still need the value of tau zero, which has to be measured experimentally, uh, or if you want to calculate tau zero from more fundamental quantities, then again you need this information of n, the value of number density of gas particles. If this is to be written in terms of more fundamental quantities, as we shall see, well, we shall only partially see. But if we just have that, we won't know the value of tau zero a priori without getting it experimentally, looking at what is the singular relaxation time, how quickly a system relaxes to equilibrium. So this is a statistical mechanics, and this is a microscopic relaxation time. And if we know that, then we can relate it to viscosity. On the other hand, we can also measure viscosity of a gas, measure number of, and if we know the number density of particles and KBT, we have an estimate also for the singular, for this value of tau zero. Of course, assuming that the singular relaxation time approximation is valid and working and is a right description of the system, right? Here we will end this and continue from the next recording.